Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to look about space radiator. How do we do thermal management in space? So let's dive right into it. Now first thing you have to understand, the sole reason Earth is even a livable or quote unquote habitable temperature is simply because we have convection. That is the one thing that is missing in space. Basically we don't have atmosphere that allows us to distribute heat from the day side to the night side. Basically that is why we have a temperature that does not fluctuate too much, because atmosphere is like carrying heat from equator to poles, heat from day side to night side, and on top of that alone would not be enough. We also have sea, which has basically undersea current, which are carrying insane amount of energy, basically like hundreds of nuclear plant kind of energy from equator to basically polar region. That's why Russia is even a place, that's why USA is even a place, because if that was not there, equator would be roasted and pole region would be frozen. So this is the reason why Earth has a livable environment. Now if you leave this place, basically let's say you get out of the atmosphere, get out of the place where you have a lot of thermal management issues, thermal management system, you reach a place where hot side will get too hot. Basically if you're facing the sun, you will get too basically scorched, and the side that is facing basically in the shadow will freeze. Now this happens on the moon, because moon has no atmosphere, no sea that can carry its thermal energy from point A to point B. So moon does not have an average temperature. So day side will go ludicrously high, aka upwards of 150 degrees Celsius. Night side will go as cold as liquid nitrogen. So understand that from boiling water to liquid nitrogen, that kind of temperature range happen if you don't have convection. Convection requires something like air or water or something, as there has to be something for convection to work. Space has neither of that. So how the heck temperature transfer happens from point A to point B? Because okay, I explained how the heck temperature is happening from Earth's equator to Earth's pole, Earth day side to Earth night side. How the heck sun's energy is reaching us? That's reaching us using radiation. This all thing you have to understand about is gamble about radiation. If you understand how radiation works, you know how to do thermal management in space. Basically the side that is hitting you, basically the sun, basically let's say I'm facing the sun, you are the sun, and you are directly hitting me. I'm getting over exposed because there is not enough molecules here in between to act as a buffer. There is no buffer, so the sun side will be overheated. However, the back side of me, like literally I could be like this and my front face will basically melt and my back will freeze, simply because my back has nothing to basically give it warmth, because there is no buffer. The atmosphere is the buffer. Atmosphere is the reason why you can have a planet that is very far and still warm, and something very close to basically sun and still be very cold, because atmosphere acts as a convection engine. If you have good convection, awesome. If you don't, you dead. So light and shadow is the critical aspect in space. Everything else falls away. Light and shadow is the main part. Now first I have to explain few rules. Now direct exposure leads to overheating, but it is directly proportional from your distance. Basically let's say overexposure that you're gonna have at sun, basically 1 AU from the sun, one astronomical unit, basically that distance of Earth and moon, that's one thing. But if you are close to, let's say in case of Venus or in case of Mercury, your exposure would be completely different. So your hot side, basically your day side, would be overheated. It will let's say in Earth's case you will only get upwards of 150 degrees Celsius, or in case of Mercury you can go upwards of 3000 degrees Celsius. So you have to understand that exposure is directly proportional to the energy source, aka in our case sun. So if you can handle the radiation from sun, you got that under control. Now because there is no buffer, we have ludicrously large temperature fluctuation. That's the first thing we figure out, how the heck you're gonna manage that temperature fluctuation. Now there are a lot of misnomer about space thermal management and a lot of other things, and I don't blame people. It's like many people say, like, vacuum, space vacuum and all that, it's cold. It's not cold. There is nothing in there to be cold. Like cold is a property of basically matter as in atoms as in vibration. If atom is there and it's vibrating, is thermal it has a thermal energy that will classify as either degree Celsius, degree Fahrenheit, or Kelvin. So that is why if you have vibration in an atom, it will exist. Now if it exists, and that's why you will have a temperature. So this creates a scenario. If you have a photon hitting something, it will always make it vibrate. Now it may be your DNA, it may be your water molecule, it may be something, but there has to be something to receive it. Without it, vacuum is a perfect insulator. It will not allow convection to go through. That is why vacuum is such a brutal place. Basically if you have fire on one place, there is nothing to dissipate the heat. If you have ice on one place, there is nothing to dissipate the cold. Vacuum is the perfect insulator. It's neither hot nor cold because there is nothing on it. And another another aspect of space you have to understand, it can only go down to absolute zero, because when you are talking everything that is submerged in the perfect vacuum, basically perfect insulator, Earth is going through a perfect insulator. So how the heck it can have a temperature plus or minus is simply because of radiation. Now every body, every person, every object, anything that you know and that exists has a black body radiation. Basically it's emitting photons. Now depending on the material, depending on the temperature, it has a spectrum. Now some would be, let's say, ultraviolet, some would be infrared, some would be basically low EM, or some would be cosmic microwave radiation, background radiation, but you will always have something that is emitting something. Once you have that, once you figure that out, basically let's say you took an iron cube and you put it in the shadow, let's say you put in the shadow of International Space Station, it will slowly over time will give off enough photon that its temperature will come down to close to zero. That is what people say when they mean space is cold. Basically over time you will freeze to death. Not instantly. Let's say I directly am exposed to the vacuum of space. The reason why I will freeze to death is not because the temperature is low, simply because water molecule in my body will seep out. Now what happens when evaporation happens? Evaporation absorbs energy. That's why you have evaporator in your air condition, evaporator in your refrigerator. Basically my body is losing gases, and that gases is basically absorbing energy to become gases, and that's vacuum is allowing that stage to happen much more faster. That's why like we will see Star-Lord is like removing his mask and like it's freezing. It's not freezing because it's cold, it's freezing because he's losing gases, and those gases, escaping gases, basically you have air canister that you and it becomes cold. That's what's happening. You're not gonna freeze to death in space because space is cold. Vacuum is flat out perfect insulator. So if I have something like, let's say even a basic cloth, I will remain hot for as long as possible, basically upwards of, depending on my black body radiation. That's why you have to study black body radiation. So vacuum is a very good insulator. You have to understand, vacuum is neither hot nor cold. Now if you are close to sun, you're gonna melt. If you are away from sun, you're gonna freeze. Now of course, if you can manage your own black body radiation and stop it from leaking, you're gonna stay fine. So everything revolves around radiation. You must understand this aspect. So that is why day side is hot and night side is cold. In case of International Space Station, there is no night side, simply because it's so close to Earth. Earth is also a giant heating element. It's like that's what we classify as greenhouse effect. Now CO2 right now, even though it's higher than normal, it still has does not have enough of a basically blockage. Basically infrared still escapes from Earth. So basically once the ISS is during the day side, basically it's ISS, Earth and sun is heating up. Now once it goes to the night side, Earth starts to heat the ISS. So ISS, from ISS point of view, everything is hot. So it has to spend a lot of energy to keep itself cool. So that is the aspect of it. Black body radiation is the reason why people classify vacuum of space as cold. It's inherently neither cold nor hot. Now once you are exposed to the sun, basically you will heat up. Depending on your distance, that will affect your temperature. Near to Mercury, you will go upwards of 4000 degrees Celsius. Far to Pluto, it simply wouldn't make a difference. You will still would be absolute zero. So first line of defense, because I already specified, we do not have anything that can act as a buffer. We create our own buffer, aka insulation. Insulation is the first line of defense. Insulation stops overheating. Basically you put a gold foil. Why gold foil? Gold is very good at stopping infrared. Basically if you have a given limited mass, basically let's say you cannot put more than 10 kilo, gold would be better than aluminum. So gold foil is very good at stopping infrared, and our sun, basically a specific star, is very hot in infrared. Basically it's giving a lot of infrared. It's not giving a lot of gamma rays or x-rays, but it's ludicrously bright in infrared. So if you can stop infrared, you can like flat out take care of most of the solar energy. It's like, okay sun, I take care of your infrared, nothing at this side, because there is not that much x-ray or gamma ray that you're like, okay, I put the gold foil and this side I'm like still melting. That won't happen because our sun is not very bright in x-ray or gamma rays. After that, you have to figure out this also stops heat loss. That happens because it is bidirectional. Every insulation there is bidirectional by nature. So if you put a insulation, basically in space industry, in astronaut industry, or whatever you have to do, we employ what we call multiple material insulation, MMR. Basically this is a very thin layer, and each layer is spaced by a spacer, maybe a mesh or maybe sometime Kevlar. We have multiple things combined and they act as a buffer layer. Now this buffer layer works in both ways. Basically it will not allow sun's heat to penetrate you, but it also means your heat won't get out. That is why we don't wear sweater in summer. Even though sweater in summer will work properly, it will stop you from overheating basically because of the sun, but your own body heat won't be rejected. That is the reason why we don't wear that. And that is why space suit then is built for operation with human. They have a lot of cooling system. Basically they have a lot of water that is circulating to keep the astronaut cool, because your astronaut by default, if it's not doing anything, it's like sleeping, it will be generating 100 watts of heat. And if your insulator is not leaking that kind of energy, basically 100 watt per hour, the astronaut will be cooked inside. So you have water circulating, and that water dumps its energy either in another water reservoir, it may have another cooling system, or flat out it may have a thermal bank. Basically like, okay, it for 5 hours I can absorb the heat, after that you must change me or you're gonna suffocate to that, because of heat, not because of carbon dioxide. Because of heat you will be like exhaustion, because it's bi-directional. Every insulator you put on yourself will work both ways. This is critical aspect. We cannot make an insulator. Now, in certain scenarios, in certain case, let's say you have something that is giving off heat in microwave radiation, you can have an insulator that like flat out blocks microwave, but lets infrared pass through. That can be done, but in our case, in normal day-to-day operation, that cannot be done. So this is the thing that pissed me off in the movie Martian, where he's wearing a spacesuit and he's like, I'm freezing. I'm like, you cannot freeze. That's the first thing a spacesuit has to do is make sure that you do not freeze to death. And like, he has a fully functional spacesuit that works in a vacuum of Mars, and he's like, yeah, I'm freezing inside a vehicle which is already insulated. So after double insulation, now that's an issue with electronics, because electronics shut down. Human body does not shut down. The human body goes to low energy mode, and that low energy is 100 watt. So even a basic insulator will keep you warm for long enough. And if you're eating, doing anything, even driving and all that, your body heat output will go up. So you cannot freeze. Like, that's the first thing. That was like, really? Like, unless you are leaking air, in that case he would be suffocating to death, he won't be freezing to death. That's like, how the heck that's happening? And he had like computer monitors, like multiple monitors. Each monitor, let's say bare minimum, is consuming 5 watts of power. That alone, 5 watt, 5 watt, 5 watt, 5 watt. He's like, he should be like warm. He should not be like, having sweat and all that, but he will not be freezing to death. Like, there is nothing to take away the energy. Radiation is not that powerful, and not to mention suits are designed with gold in mind. So they can make sure that infrared does not escape us. Now, of course, no insulation is absolutely perfect. Over time, let's say you are dead and your body temperature was 30 degrees Celsius, it's not going to remain 30 degrees Celsius forever. But if you are alive, your spacesuit, even a basic one, will keep you warm for more than long enough, even if you are like, let's say, in the dark side of the moon. So that was like a really, really crazy to see. Then we have to understand this. In space, you are more likely to boil to death than you are freeze to death. We have to employ basically infrared based radiator. That is why ISS has such a huge radiator. Now, if you are not gaining the size of this radiator, understand this way. This is bigger than a truck, one of these. And there are 3 of these on one side, one and then another. And even in a big thing like space shuttle, the whole door inside of that cargo bay door had radiators put into it. Because when you have something this big and you have humans inside it, you have to take care of the heat. Now, in case of satellite, there is not enough energy that is happening, because you might, even if satellite, let's say, is like few kilowatts, most of the energy is spent in radio waves. That's why it's not basically melting itself. But in case of human, we are melting ourselves, so we have to have giant radiators to save ourselves. Now, all the radiators are white simply because of one thing. They have to make sure that sun itself does not end up imparting energy into it. That is why they are coated white. Now, if they are very far away, let's say as far as Pluto, they will be black. That's why RTGs always are black. RTGs are generally used when they have to be sent on very far missions, so they generally are black. So generally we have to make it like a compromise kind of scenario, because a radiator, basically, if it will have 2 sides. Side that is facing the sun will be shut off. The side that is facing the basically night side, or aka shadow, will have a lot of coolant going through it and dumping its energy in infrared spectrum. The gases or whatever the coolant that is selected, that is done such a way that it can dump most of its energy in infrared spectrum. You really want that. Like, most of the thing you have to make sure everything gives off infrared. You just want to find a coolant that is very efficient at it. Like, it can absorb a lot of infrared and dump a lot of infrared. Everything is about surface area. Now, here the surface area, like Earth, will not work. Basically, you cannot have one radiator on top of another and another. It will not work, because they will end up radiating each other. So that is why convection design radiator simply does not work. You simply have to have one flat piece. And if you have multiple of them, you have to make sure they are not casting heat from one another. So this is very critical. And if you, let's say, have 2 of them in case of space shuttle, so the night side will be more efficient because it's not getting exposed to the sun. Now, we do design it such a way that even if it's fully exposed to the sun, it will not get overheated, but generally you would try to avoid it. And like in case of Parker Solar Probe, the radiator that it has, because at that distance X-ray and gamma rays is big enough that even though you can have giant thermal shield, it will still have enough of the radiation that will make through the heat shield that your components will heat up upwards of 200 degrees Celsius. Now you have to dump that kind of heat, you have to have radiators, something like this. Now that radiator is faced perpendicular. Basically, if sunlight is coming like this, they will have radiator like this. So radiator is not as well. If they did like this, the radiator will end up acting as a heating unit. So radiator is very crucial aspect. BFR will also need radiators, or they may have a, like if you don't want radiators, you can do one thing: dump all that heat into something and expel it outside. Basically boil water with that heat and then just let the water go. You can do those kind of basically evaporative cooling. But other than that, you have to have radiators. Basically in International Space Station or something bigger than that, something like let's say a Starship Enterprise or things of that nature, if you have hundreds of people, you are more likely to roast yourself than to freeze to death. I have no idea why the heck everybody like space is cold. It's an insulator. Then we come to the aspect, then why the heck everybody is like talking about heaters and all that. First you have to understand, all of our electronics generally have a hibernation system. Let's say talk about the probe that went to Pluto. First, it's way too far from sun. Flat out is very far from sun. Like if you stand on Pluto, you will have a hard time finding sun because it will literally look like just a bright star. So during that hibernation, no computer processor is running, the radio beacon is only running and minimal power at that. So that inherently means whatever energy source you have, let's say this RTG, it's barely giving you few, basically even though it's giving you 500 watts of energy, you're not using it. So it's just like disconnected. So that means this part will freeze. Basically, even though it has insulator, no insulator is perfect, but it's not like human body where it has like 100 watt of continuous power. So during that off period, that the temperature goes down. Now many instruments like cold temperature, like infrared sensors, camera sensors and all that, they love cold temperature. Battery flat out hates it. Battery is like, dude, if you drop me below 5 degrees Celsius, I'm done. I'm like this. I will not start again. So to make sure that during those times, basically when you have hibernation, equipment is not generating heat, you have to provide heat. So how do we do that? Basically we have something like this, very small cylinders, these which has a plutonium oxide in them, and it acts as a 1 watt heater. And that's it. The reason why we use this is simply because at that distance we don't have enough solar power, and this will not break down. Basically, of course it can break down over, it has half-life, so it's not going to produce 1 watt of power 24/7, but it will keep working for more than 10 years. So you can understand, even though we are putting plutonium, we are only giving heat output of 1 watt. The reason why it's so little is simply because it should be there to like A, keep the battery from freezing, B, it should overcompensate for the heat loss of the insulator, because no insulator is perfect. It's gonna radiate, black body radiation will still happen, but if you have let's say insulation is losing half watt, you will add 1 watt to make sure it never goes down below a certain threshold. Now battery flat out does not lock out, and on top of that, power management is issue. Think of it this way, like all the rovers that we sent on Mars, during night time they flat out shut down simply because their cameras could not see anything, so they flat out shut down. During that time they have no power source. Basically solar cells are not working, battery, if the temperature goes down beyond a certain point, will stop working. So they had this sort of thing, hundreds of this. Now in case of Cassini probe, 100 plus was used to make sure the critical components always remained above a certain temperature, and these also acts a very good basically temperature reference. So that is why we have to figure out heaters. Generally when you are talking about human or anything big and bulky like a space station or things of that nature, you have to worry about cooling. When you are talking about something low power like satellite, because even though it's consuming, like it may have solar panel that is like 10 kilowatt or 20 kilowatt, most of its energy is converted into radio waves, so it itself may drop down temperature drastically. But generally if the insulation is good enough and you're close to sun, you don't have to worry about heating, you have to worry about freezing to death. Basically you don't have to worry about getting rid of excess heat. So power management is the case. Generally, let's say in case of Saturn missions, you had liquid oxygen into the tanks, and because our sun is not very bright in X-ray or gamma rays, the white paint and the material coating used flat out stopped it from heating the basically fluid. Consequence, the fluid ended up freezing. Basically liquid oxygen ended up freezing in a solid stage, so they had to add heaters there to make sure that it's never frozen solid. So that was also an issue with SpaceX Falcon 9 Heavy, basically Falcon 9 Block 5 Heavy edition, where they had like, if it was sent very far off, it may freeze. Basically the fluid may freeze simply because evaporation is also happening. So we have to do power management. It's not something that you can be just like, okay, we're gonna make sure it's always hot, it's gonna stop working, we're gonna make sure it's cold. Now processor will like the cold temperature, camera sensor will like the cold temperature, most things will like cold temperature. Heck, we use liquid nitrogen for overclocking. Most things will like cold, but the moment it touches the battery is like, no, I'm dead. And thermal sensors also need a reference point. So that is why we have heater. I have no idea how the heck this made into a movie, like a big budget movie of Martian, where it's like he's an astronaut wearing a spacesuit. The first thing of spacesuit is like, make sure the astronaut does not freeze to death in space. He's like, yeah, I'm freezing. I mean, you will not freeze. Like, your first line of defense is good enough. And given the fact that these things go into hibernation, human body does not go into hibernation. And then he was inside a vehicle, which itself would have been insulated. So it's like, how can you freeze? Inherently, how can you freeze? Now, of course, if you are in Europa, you can freeze there. Why? Because there is atmosphere. Atmosphere can zap energy away from you. But in case of Mars, nothing will happen. There is nothing that can zap energy away from you. So I really don't like this. Like this kind of thing really bothersome. Is like, you have giant spacecraft, everybody is freezing to death. Dude, your body is 100 watt. Vacuum is a perfect insulator. If you have a lot of people gathered in one place, like let's just say they're corpses, it will take years to cool down. Years. Not days, like, oh, vacuum happened and everybody is freezing to death. It's frustrating to deal with, basically. So I would urge you to study radiation to understand these things. So this was my ranty presentation about space thermal management. I hope you liked it, learned from it, or had fun. In that scenario, please click the like. If you didn't, don't worry about it. You can press dislike. I would urge you to press this twice to show me your extra disappointment, and leave a comment because I reply to all of them. Press subscribe, press the bell icon if you're free, and as always, thanks for watching.